Hello, welcome to Physics Chapter 10, Lecture 1. You're going to need your note printout for this lecture and open in your book to page 323. That's the first on your own problem you're going to work. So today's lecture is about springs, and that's most of this Chapter 10 is about springs. Now, springs exhibit what we call periodic motion. That's regularly repeating motion. So we've already had a chapter in Chapter 7 about uniform circular motion. That's periodic motion. We talked about how the planets exhibit periodic motion, did some math on that. A pendulum does, and we're going to hit that at the end of the chapter. And then a spring, we're going to look at how a spring works. So, you think about a spring, something like that, and we put maybe a hook on the end, and we've got a mass that we hook to that spring somehow. All right, and that spring, if you put a mass on it, the spring is going to stretch. And it stretches according to Hooke's law. All right, Hooke was a scientist that did a lot of different kinds of research, including on springs. And Hooke's law, and you've got a space on your notes, is to write this: force is equal to the spring constant K times the distance that the spring stretches. Okay, so the force is the restoring force supplied by the spring. Okay, so and K is a constant that is going to be different for every spring based on how the spring was manufactured, how thick it is, what kind of materials were used. And of course, and that doesn't change for that spring. And then the distance or displacement that it stretches is also part of the equation. The force applied by the spring will always be opposite in direction of the spring's displacement. So if you pull a spring down, then the force is going to go up. It's going to resist and try to pull it back upwards. If you compress a spring, then the spring is going to push the opposite direction of the compression. So equilibrium position is when no net forces are acting on an object. So if we put a mass on a spring, it stretches and then it goes still. You're in equilibrium position. Now we could pull on that mass and displace it and get it out of equilibrium position, but equilibrium position is just that point at which the spring no longer has any net forces acting on it. It's kind of reached that point of stillness. All right. The strength of the restoring force is directly proportional to the displacement. All right, so the more you pull it down, the greater the force. All right, and that makes sense with the math here. If I increase delta x, if this number stays constant, then the force is going to increase. All right, so in class, I always have a spring demonstration where I put a mass on a spring, and it's really easy to see all this. Not so easy to do on a video, so I am going to in the description box, you need to watch the video that I link. And that'll give you a good idea of what equilibrium position is, and also the amplitude and the period of a spring and things like that. So it's just a 6-minute video. I'm going to put in a link in the description box. And if you're not getting to be in the in-class lecture for this, then that'll really help you understand how a spring works. So let's look at on your own 10.1. So we're in the book on page 323. So it says, when a student hangs a 25-gram object on a spring, it stretches 3.45 centimeters down from its equilibrium position. What is the spring constant? And we won't worry about the second part. Is it weaker or stronger than the spring in example 10.1? Example 10.1 is this blue example. It'd be great if you're not going to be in class and you're learning this on video. It'd be a great example to read. All right, so we have Hooke's law equation, F is equal to K delta X, and we are solving for K. What is the spring constant? So K is going to be the force over the displacement. Okay, so force in this case is just the weight. All right, that's what's pulling down, and weight is going to be mass times gravity. All right, that we've used in previous chapters. All right, so mass is 0.025 kilograms, so we've got to change that from grams to kilograms. Gravity, 9.8 meters per second squared. And then the distance we need, because gravity's in meters, the distance we need to change from centimeters to meters. So that's going to be 0.0345 meters. All right, 3.45 centimeters, divide that by 100. So K is going to be 9.1, and the unit would be newtons per meter. It's a very weak spring. All right, let's look at 10.2. I think we can fit this on here. So 10.2, if you'll follow along, is just underneath 10.1 there. A physicist hangs a 412 gram object on a spring whose spring constant is 11.91 newtons per meter. How far does the spring stretch? So this time we are solving for delta X. So once again, we start out with Hooke's law. F is equal to K delta X. So rearranging algebraically, delta X is going to be the force divided by the spring constant. The force, again, is just the weight. And so that is mass times gravity divided by the spring constant. All right, so delta X, let's plug those numbers in. 412 grams would be 0.412 kilograms. Gravity is 9.8 meters per second squared. And then it says the spring constant was 11.91 newtons per meter. All right, plug that into the old calculator and you'll get 0.34 meters. That's 34 centimeters, quite a stretch. That's quite a long spring there. All right, so that's just some basic problems concerning Hooke's law. All right, let's turn to the next page of your notes. All right, we'll leave Hooke's law there, and the next concept is amplitude on your notes. So that's the maximum distance away from equilibrium position in periodic motion. So again, it's important that you watch the video that I linked to in the description box. But amplitude, let's say you were to pull this mass down and let it go, and let's say you were to pull it down 5 centimeters. Then the amplitude would be 5 centimeters, the maximum amount that you pulled it down. When you let it go, it's going to oscillate back and forth. All right, and the oscillation will over time get shorter and shorter, but the maximum amount, the amplitude, would be the distance that you pulled it down before you let it go. So again, watch the video, but now springs exhibit simple harmonic motion. Okay, so that's where period is independent of amplitude. So we're going to do a lab that demonstrates that, and I also demonstrate it in class. But if I pull down 5 centimeters, a period is the time it takes to go up and back down again, okay, to get back down to its original amount that you pulled it. So it goes up and then down. That's one period. It's a period of time. That's the time it takes. So if it's simple harmonic motion, then if I pull it down 5 centimeters and it takes the time that it took to go up and down was 1 second, if I pull it down 10 centimeters, it'll still be 1 second because you've increased that force. If you pull it down further, all right, the spring, it gets harder and the spring pulls with a greater and greater force, so it's going to make it go faster. So simple harmonic motion is period or time is independent of how much you pull it down. If you pull it down half as much, say 2.5 centimeters, the period would still be 1 second, the time it takes to go up and come back down again. All right. So at amplitude, okay, so when you pull it, the mass all the way down, at amplitude, velocity is equal to 0 and your acceleration is maximum. You need to memorize that. And this is on page 328 in your book. All right, very important. At equilibrium, that's where your velocity is max and your acceleration at that point is 0. Okay, again, the video should help you, but the period for a spring, and we use T to denote period, is 2 pi times the square root of the mass, that's the mass that's on the spring, divided by the spring constant. So you'll have to memorize that equation just like you'll have to memorize Hooke's law. All right, let's take a look at 10.3. Okay, it says, and we're on page 333 here. So I'll bring this into view. It says an 11.2 kilogram mass is attached to a spring. When displaced from equilibrium, it bounces up and down with a period of 2.3 seconds. What is the spring constant? Okay, so we are solving here algebraically for K. All right, so I'm going to just solve it with our variables first, then we'll plug the numbers in. So we have, now what I would do algebra-wise is bring the 2 pi underneath T, or the period. Now we're going to, in order to get rid of the radical, let's square both sides. Okay, if we do that, we would have T over 2 pi all squared, and then the radical lifts when you square this side, and you just have m over k. Now solving for k, if we multiply both sides by k, that'll eliminate the k on the right side, and you would have k is equal to the mass divided by this quantity T over 2 pi all squared. Don't forget to square that. So K is equal to the mass. Let's plug that in. That is 11.2 kilograms. Pretty heavy to put on a spring. Probably the biggest springs that might be where you live would be in your garage door. If you look right above the top of the garage door when it's closed, you'll see a really big, thick spring, and that's to assist you in opening that heavy door. All right, the period is 2.3 seconds. And then 2 pi, and we need to square that. All right, so if you put that in your calculator, go ahead and give that a try. You'll get 83.58 newtons per meter. I would call that an average strength spring. I think the one that we work in our lab is around 50, so a little heavier than that one. All right, let's do 10.4. So 10.4 says when it supports a 351 gram mass, a certain spring stretches 12.1 centimeters. If the mass is pulled down 5.1 centimeters from this new equilibrium position and then released, what will its period be? Okay, so in this case, they didn't give us K, so we're going to have to solve for K first. So we know that F is equal to K delta X. So K is going to be the force divided by delta X. All right, so the force is just going to be the weight. All right, and the weight is going to be mass times gravity. All right, so plugging those numbers in, the mass is 0.351 kilograms. Gravity 9.8. And then the distance is 12.1 centimeters, so that's 0.121 meters. All right, so that's going to be 28.43 newtons per meter. Now let me talk about this number here. You're going to use, to find K, you have to see where it stretches when you initially put the weight on. How far does it stretch? The additional amount that you displace it by pulling down, all right, you're pulling down on that spring, that doesn't factor into K. You're adding an additional force. K is determined through the initial displacement when you first put the weight on. That's really important. Don't use that 5.1 centimeter number right there. Now we're going to use, we found K. The 5.1 centimeter actually doesn't even figure into this problem, all right? So the T, or the period, is 2 pi times the square root of the mass, 0.351 kilograms, divided by 28.43 newtons per meter. All right, if you plug that into the old calculator, you get 0.7 seconds. All right, seems reasonable. Okay, and then the last problem that we will work on this lecture is on your own 10.5. So it says, what would be the period of the mass in problem 10.4 if it were pulled down 10.2 centimeters away from its new equilibrium position instead of 5.1? Well, it's going to be exactly the same. The amount that you pull it down with that additional force away from equilibrium is irrelevant to the period. Okay, the period doesn't include a delta x in it. It's just 2 pi times the square root of m over k. So with simple harmonic motion, period is independent of amplitude. So it's going to be 0.7 seconds. All right, so that does it for Chapter 10, Lecture 1. We'll continue to talk about springs in the next lecture and also talk about pendulums. So I'll talk to you then.